Today we're going to look at a really nice, simple, elegant, really beautiful proof of Pythagoras' theorem. And you need this. You need to know this because imagine the following scenario. So we want to imagine, okay, you're giving a talk about geometry or something, and it's going really, really well. Everything's going great. And then some guy in the back row raises his hand. You say, okay, what's up? And he starts telling you, he asks you something like this. Hey, man, you use Pythagoras' theorem a lot, man. So why is it true? Can you prove it? And you kind of just stand there thinking, yeah, well, everyone knows it's true, and I've proved it before, but I can't remember how to do it. And then everything starts going down the drain after that. So you've got to know a good proof of the Pythagoras theorem. And I have it's a well-known proof, but it's my favorite one. It's very, very beautiful. And why is it beautiful and elegant? I'll tell you why. It's because this proof uses similar triangles, and similar triangles are really the most fundamental idea of classical geometry. And there's really nothing more than similar triangles in this proof. And in fact, in very, very many geometry problems, similar triangles are really the only thing that's going on under the hood, And, I will have more to say about that. That's kind of my view of classical geometry. It all boils down to similar triangles. Okay, so what are similar triangles? So here we have some similar triangles. These two triangles just happen to be similar. Why are they similar? Let's see. Well, there's the three angles are the same. So alpha. If two of the angles are the same, okay, well, if two are the same, then the third angle, let's call it gamma. Gamma has to be the same. So all three angles are the same, and so they're similar. Now, we could write it like this. Triangle ABC is similar to triangle EFG. And just sort of, write it off the top of our heads like that. That's sort of true. But writing it like this without careful thought is going to cause you problems later on in your reasoning. And, in an upcoming video, I'm going to do something with similar triangles that causes me and a lot of other people in mathematics to really pull our hairs out, because it's so easy to get the correct correspondences between sides and angles of similar triangles in a more complex setting. It's can be quite confusing. Now you have to practice this, you see. So we're not going to do this. We're going to be a bit more careful about things, and we'll see why this isn't. We should not just write it off the top of our heads like this. So ABC. So point A correspond to angle alpha, and B correspond to angle beta, and C corresponds to gamma. And we should be careful to preserve this correspondence here in the next triangle. So what is alpha? Alpha is not E, it's F. It begins here, alpha, like this, you see. And then beta, that's point E, that corresponds to beta. And then G corresponds with angle gamma. Okay, and that's very nice. So this is a more careful and more considered way of doing things. And now we can make corresponding sides. There's we can write something like this. The side AB. Now AB, let's get some color. AB is opposite angle gamma, you see. It's opposite to angle gamma, AB. So AB, we can put little marks for the angles all over the place. It's going to clarify our thinking. It's going to look a little weird but it's going to clarify our thinking. So side AB correspond with angle gamma. What side corresponds with angle gamma in the second triangle? Well, correspondence is with side FE or EF. You see, that corresponds to gamma also. And okay, how about AC? AC is what angle? Well, it's opposite this angle here, beta. So, but you see, beta is opposite AC. So put beta here, then it corresponds very cleanly with FG. FG is the beta side. Let's write that better. FG like this. And one more. Okay, so how about BC? BC corresponds with angle alpha. So BC is this side, corresponds to angle alpha here, the opposite angle. Okay. And this correspond in the second triangle, it corresponds to this angle alpha, corresponds to this side EG. So that's also alpha. Okay, very good. So why am I doing this? Well, it makes it a lot easier. Okay, let me write that down. So writing all the angles and being careful about the angles makes it much easier to correctly write down the proportionality relationships and expressions in similar triangles. Okay, so let's write down some of these. Okay, so I copied that figure over here so we can have it as a reference. All right, so on this left side, we'll work with this triangle. On the right side, we'll work with the bigger similar triangle. And these two are similar, so we can put that symbol. So let's look at some ratios of sides. Let's look at AB over, okay, AB is, be careful, that's gamma. And let's say BC. BC is over here. So we have AB, BC is over here. BC corresponds to alpha. So then what is going to be the correct ratio on the other side for the bigger triangle? Well, it's the gamma over the alpha, yes. So you see, it's really already helping us. Gamma is EF like this, and alpha is here, is EG there. So we correctly write down relationship, and we're not going to get it wrong because we're careful about what angle corresponds to what side and so on. Now, that's great. So this is similarity of lengths, but we also have similarity of areas as it's proved in Euclid. So let's write the areas. We'll use square brackets, ABC. That's the area of this triangle here. And then we'll have the area of the bigger triangle is EFG. And the areas also are involved in proportionality relationships. So ABC, the little one, okay, and we divide by, let's take gamma, for example. Gamma is side AB, yeah? Okay, and AB squared. So the proportionality of areas will involve the squares of the sides. And this is going to be equal to EFG area, and divided by what? Well, it's the gamma angle side. So what does correspond to the gamma angle side? That's EF squared. And so on. So we can write many relationships like this, okay? And as long as we keep track of the angles, everything's going to be correct. Now, this is, we need this type of area relationship for similar triangles. We need that for our proof. Okay, so now that we have that all sort of figured out, let's now begin our proof of Pythagoras' law. we are going to prove it for this triangle here. So again, we have this convention in classical geometry. From A, we have vertex A. The little a side will be opposite vertex A. That's how it's usually labeled. So opposite big B vertex is little b side, and opposite C is the side C. And I'll be a bit clear here. The side C is this long thing from A all the way to B, like this. And now we can start messing around with angles. So this is going to be 90 degrees. This here is, let's call this beta. And if that's beta, then this angle is 90 minus beta. Okay, great. And what's then this angle here? Well, this angle C is 90. This is 90 minus beta. So this has to be beta, because beta plus 90 minus beta is 90. So that's got to be beta. But this is 90, and this has to be 90 minus beta. So what we see is we have these similar triangles inside. Okay, look carefully here. Look at this little triangle. The angles are beta, 90, and 90 minus beta. Now look at this bigger triangle here. In the bigger triangle, the angles are the same, 90 minus beta, beta, and 90. Okay, and so these little triangle, the little one, the medium one, and the really big one, they're all similar. And now we can write down similarity relationships very carefully, with all the little angle labels. So triangle ABC, that's the really big one. That's the outer triangle, triangle ABC. So this is, if I label it 90 minus beta, beta, B is beta, and then C is 90. Okay, and that will be similar to the small one. The small one is, okay, so A is 90 correspond to 90 minus beta. That's B, that's this side here. Okay, yeah, okay. So C, 90 minus, okay, 90 minus beta, 90 minus beta, okay, I get it, okay. 90, and then beta is B here, vertex B here. Okay, we did this one. Okay, B is beta. And then finally the 90 degree one, that's D, CBD, like that. And okay, one more. So, all right, so 90 minus beta in this yellow triangle, in the medium side one, that's A, correspond to A here. So that's 90 minus beta. And then what corresponds to beta? That's the vertex C, that's the one over here. Okay, so that's beta. And then finally, D is going to be my 90 degrees one. There, I have these beautiful relationships or similarity. They're all similar because all the angles are the same. And now I can use my area similarity relationships. Okay. All right, so for the first one, the area of ABC, that's the big one. Well, we can take that and divide it by the 90 degree side. What's the side corresponding to 90 degrees? Well, C, in the big triangle ABC, the side corresponding to 90 degrees, this is the 90 degree vertex, and the side corresponding to 90 degrees, that's C squared. Okay, that's C, and we have to square it, and we get C squared. Here, the next one is the tiny little one. That's CBD, area CBD, divided by, okay, we want the 90 degrees side, because it must correspond. They must all be correspondingly the same thing. So what corresponds to 90 degrees? Here's the 90 degree angle, and it's A, so A squared. So opposite that angle is A. Okay, now ABCD. It's so easy to make a mistake. Okay, okay, ACD, what corresponds to 90? Okay, this is my 90. B is the one that's on the opposite side, so B squared there. And so we get this lovely relationship of areas. Okay, and we do a little algebra now and see what happens. So let's solve for the areas in terms of the big one, ABC. We get CBD is A squared over C squared times ABC area. And then ACD, this is B squared over C squared ABC area. We have one final relationship that we can use. And what is that? Well, the area of the big triangle, area A, this one here, let's use some color. This one here, this area here, this is equal to the little area plus the middle-sized area. Okay. And that's the key to everything. So we have ABC is equal to CBD plus ACD, like so, ACD. And now all we have to do is plug these things in. So I plug this into here, and then I plug this guy into here. And I'm sure you can already see where this is going. It's a very, very, very nice finale to this thing. So ABC, this is equal to A squared over C squared ABC plus plus B squared over C squared ABC. Very, very nice. And look at this. This all cancels out. This gives me 1 here. This cancels out. And I end up with 1 is A squared over C squared plus B squared over C squared. And finally, C squared. Multiply everything by C squared. C squared is A squared plus B squared. I think that's really, really beautiful. I wanted to do a vid on this because it's such a lovely theorem. It's such a lovely proof. I mean, it's so beautiful. I'm in awe at how elegant this is. And it only really uses similar triangles, okay? And similar triangles are a fundamental concept in geometry. I mean, other proofs of Pythagoras' law use very clever constructions, like that thing with the rectangle and all that. Okay, that's very nice and all that, but this uses just fundamental reasoning of geometry. So I really, really like this proof. And well, if you like this video, then click like. Clicking like actually seems to do something in YouTube. It has an effect, so please do it. It's very effective, more than I thought. And subscribe, of course, because the more subscribers I have, the better it will eventually be for me producing videos. I can spend more time on it. I can do better stuff and do more research into interesting topics and all that, you know. It's something I'd like to do. So it would be great if you click like and subscribe. Okay, I hope you enjoyed this, and I will see you next time.